Alright, so we want to talk about differentiability and continuity today. Let's warm up with a little bit here with a step function. Okay, we're going to find the limit as x approaches c from the left and from the right of these things. Okay, so the slope as we're approaching c from the left, now they put c at 0. Okay, so c is 0. Actually, we should just, there's c equals 0. Okay, so the slope, what is the slope approaching as we approach c from the left?
0. Well, actually, yeah. From the left, it's going to help.
If I'm approaching from the left, I could be doing this, 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 this.
Oh, it's not.
So what's it approaching?
Oh, undefined, right? Let's keep getting positive and
Yeah, it's approaching positive infinity.
undefined.
Okay, so the limit does not exist. Yeah, it's undefined. Okay. As we approach from the right-hand side, we have from here to here to here. What's the slope as we're approaching from the right-hand side? It's 0. Okay? Because, yeah, we could start further to the right and go here, but then it's going to jump down to here and be just horizontal as we're approaching from the right-hand side. So this limit is going to equal 0. Okay? Now, what did we say yesterday about a case where, about the derivative, when the limit from one side was approaching infinity? Huh?
Doesn't exist.
Yeah, the derivative is not going to be defined at that point. Okay? So actually, in this case, the derivative at 0 is not defined. Okay? Now, that leads us in here to what we're talking about today. Okay? So, differentiability and continuity. If I were finding the slope of this secant line, I'd use this slope definition that we've been using. Okay? There is an alternative limit form of the derivative. And notice here, instead of using delta x approaching 0, we're actually having x approach c. Okay? So we want the derivative at this point c f of c, and we're going to move this point f of x along the function so that x is getting closer to c. Now as x is getting closer to c, what's x minus c approaching?
0.
0, okay? That was delta x approaching 0. Here, x is approaching c. This is an alternative form of the definition of a derivative, and it can be useful in some places, okay? Now, this requires that the one-sided limits exist and are equal, okay? And we could call these the derivatives from the left and the derivatives from the right. Okay? F is differentiable on a closed interval AB if it's differentiable on the open interval AB. And if the derivative from the right at A and the derivative from the left at B both exist. This is kind of the same idea as continuity on a closed interval. It's got to be continuous on the open interval and the endpoint has to equal the limit on both sides. Okay? You can't have like a jump on the end. Well, here we can be differentiable on a closed interval if it's differentiable on the open interval, and if the derivative from the right and the derivative from the left both exist. Okay. Now, so there are basically three cases where the derivative will not be defined. It's not differentiable at a point, okay, if one of these three things happens. First of all, if it's not continuous at that point. All right, we saw that with our step function just a moment ago. On one side, the derivative would be approaching infinity. Okay, we have this non-continuous function, so it's not continuous. Now, here's the thing. You could take the derivative of a step function at a half, or 2.2, or something like that. You simply could not take the derivative at any of these discontinuities. Alright? Likewise, a function is not differentiable at a point if there's a sharp change in direction. Okay? We would say it's not smooth. Alright? So here, the absolute value function is a good example of that. This one has the point or vertex at the point 2, 0. So this is not differentiable at x equals 2. It is differentiable at 1 or 0 or any other value of x, just not at 2.
Is that the case for anything other than absolute value? Or is there no other graphs like that short?
Well, no, there are other graphs, and particularly like with piecewise functions, that's something that you would have to be very, very careful to see, is it differentiable at the end point, or at the, you could say, the junction between the two parts. And basically what ends up happening with the piecewise function is you would take the derivative of both parts and make sure it was equal at that point. Okay? If one was a half and one was 2/3, then there's a point there. It may not be as obvious as that one is, but there's a sharp change in direction.
If it's like an endpoint, which like rule would be used at which? Would you say 2 because there's kind of sharp change, or would you like say endpoint even though it's not?
Well, continuity.
Would you, okay.
I think that would fall under continuity. It's not continuous from the other side. Yeah, like with the radical function, the endpoint there, it's not continuous through the point. The other case is when the tangent line is vertical. And actually, you know what, that would fall under this category, sorry. Remember we said the tangent line, as you approach 0 on the radical function, is going towards positive infinity. Okay? So you are getting a vertical tangent line. And that's, at that point, the derivative would not be defined because the slope is undefined for a vertical line. Okay? So those three cases here are the cases that you need to keep in mind, and you can tell simply by looking at a graph certain values that the derivative is not defined for. Okay? Now, here is one theorem as we are talking about continuity. Remember, to prove that there is continuity at a point, you have to prove that the left-hand limit and the right-hand limit are equal, and that the function is defined and equals that same value. Okay? So the limit exists if the left and right hand are equal, but it's only continuous if the function also equals that value there. A simpler way here, that if we can prove that something is differentiable at a point, then we automatically know it is going to be continuous at that point.
So pretty much, if it has a limit that exists coming from the right and the left, it's differentiable unless it's a hole.
Unless there's a hole, yeah.
Okay.
Yeah. Okay. And that's where things that we learned in the last unit there about continuity, like all polynomial functions are continuous for all real numbers. Those functions like the trig functions that were continuous for everything in their domain. Well, that means we could take the derivative for any value that's in its domain. So, tangent, as long as we're not doing it at negative pi over 2 or pi over 2 or any of those asymptotes, we can find what the derivative of tangent is at any other value. Okay? So, here's kind of a summary. This only works one way. Differentiability, if we know it's differentiable, then we know it's continuous. So differentiability does imply continuity. However, it's possible for a function to be continuous at x equals c and not be differentiable. Like the absolute value function and the one here with this vertical tangent. Those are continuous, but they're not differentiable. Alright? So, differentiability implies continuity. Continuity does not necessarily imply differentiability. Okay? Make sense? Alright. Alright, actually let me go ahead and use the alternative form here. I'll do 74 real quickly, okay, as an example. The alternative form says that we have the limit as x approaches c of f of x minus f of c over x minus c. Alright, and here we're finding c is 1, so we're actually finding f prime of 1 here, guys. Okay? So, if c is 1, f of c, or f of 1, is 1 cubed plus 2 times 1. So 3. Okay? So notice here, as x is approaching, we're going to be doing this, the limit as x approaches 1, we have x minus 1 on the bottom. F of x is x cubed plus 2x. And we're going to subtract f of c, which is 3. Okay? So we have the limit as x approaches 1. We factor. Might have to get a little creative with the how to factor, because this is an x cubed, right? So if you probably won't be able to factor that in your head, but what should be a factor? X minus 1. Hopefully x minus 1 is a factor, right? Because we want it to cancel with the one on the bottom. Alright? And that's over x minus 1. That's going to end up canceling. The question is what's left over. Do you remember how we can do that?
Oh, we can just divide by x minus 1.
Divide by x minus 1. Use either long division or synthetic division. Remember synthetic division?
Yes, sir.
We have a 1x cubed, 0x squared, a 2x, and a minus 3. We're going to divide it by an x minus 1, so I put a 1 in here. And then I add down, and I multiply by this 1 over here. So 1 times 1 is 1. I add down, multiply by 1. I add down, multiply by 1. And I add down. And this started out as an x cubed, x squared, x, and those were the numbers. This is now the x squared, the x, the number, and then the remainder. Okay? So what goes in the parentheses? X squared plus x plus 3. Okay? And now that I can cancel out the x minus 1, which, by the way, this had to end up being a 0 or else it would have messed stuff up, okay? We knew x minus 1 needed to factor out of that in order to cancel, so we're glad that we saw a 0 here. But now that we've done that, we can actually plug in 1. 1 squared plus 1 plus 3 is 5. So the slope of that x cubed plus 2x at 1 is 5.
So when you write f prime of 1 equals 5?
Yeah, f prime of 1 equals 5. So you see it's a similar process to what we did before with the delta x approaching 0, but there's a little bit of an alternative here. The nice thing about this method is that we didn't have to do x plus delta x cubed, you know?
So the alternative form is that f of x minus f of c
Over x minus c, and x is approaching c instead of delta x approaching 0.
But that's different than what we learned 2 lessons ago, right?
Yeah. Yeah, there are two forms of this limit definition, and you can use either one. The delta x is typically simpler, but this one is useful in certain cases, so we want you to be familiar with both.
Could you have done that with the